Hello everyone, welcome to this series of problem solving fundamentals. My name is Ashish and today we'll be talking about time and space complexities. Now this is going to be part 2 of it, and if you haven't watched my part 1 video, I'll put that link in the description box below. Now in this video, I'll be talking about these 5 things with you. What is big O notation, time and space complexities general rules with examples, time complexity for non-recursive functions, followed by time complexity for recursive functions, and at the end, we'll be talking about the edited master's theorem for interviews along with a pro tip. So stay tuned to this and let's get started. So, what is big O? So it's an asymptotic notation which defines the upper bound for a given algorithm. Let's take an example. Suppose that we have taken an example of binary search. Let's say there is a binary search algorithm which takes log of n time. Now you might have heard of binary search takes log of n, but let's see how it is. So when we say binary search is taking log of n time, that means binary search algorithm is taking log of n at the worst case and not at every case. Example, let's say we have an array of say 1, 2, 3, 4 and 5, and we need to find 3 in this case. So at that case, binary search is going to take O of 1 time because it's the midpoint and can directly find it in a constant time. So what I'm trying to say here is, when we are mentioning about log of n as a complexity, it's the worst time complexity and not the best time complexity. Let's take an example apart from this coding. Let's say you have in your account balance, let's say person A has account balance of say 0 to say 1 lakh, and he maintains his balance from 0 to 1 lakh. Maybe he can maintain 1000, he can maintain 50,000 or 1 lakh. Now the person's A's bank is hacked by, let's say, a thief person B. Now suppose he has at current balance of 1000 and B hacks it and B takes all the 1000 rupees. Now suppose he has 0, so in that case B will have only 0 rupees. He cannot hack more than 0 rupees, right? For example, one has 1 lakh, A has 1 lakh rupees in his bank account. So at worst case he can have 1 lakh in his bank account and everything will be stolen by person B. So 1 lakh becomes the upper bound for this case. Similarly, when we are saying about log n being the upper bound of it, that means when given an input n, we can have any value starting from n becomes 0 to infinity. The complexity should not exceed the time of log of n. So that becomes our worst time complexities. Similarly, we can have worst space complexities. And that's why we need, or we denote the big O notation. There's something called as big omega, which defines the lower bound, and there's something called as big theta, which defines the tight bound, and you can obviously read about these in books. So that's how we use the big O notation. Now before even starting off with finding the complexity of a given code, let's have a look at some general rules. The runtime of the program should be equal to the running time of all the fragments of that program. Now if you're not getting it at this point, don't worry, I'll be explaining everything with proper examples. Rule number 2 is drop all the constant multipliers, then drop all the lower order terms, always go for larger inputs, and find the worst case time complexities, which is basically the big one. Let's take an example and see what all everything means. So now let's take a simple example. Suppose this is the given code. So as per the general rules, what is the first thing? We have to find the runtime of this function, and which is equal to the runtime of fragments of the code. So what all are the fragments of this code? So let's see, this is the first 2 lines is something which will take a constant time, because these things which are like one-time operations and which do not depend on the input, so that will take O of 1, you can say. So this is 1 plus 1 is 2, or okay, you can say it will take O of 2 time. Now this is having 3 loops, which is everything is going from 1 to n, and this is going for n cube times. So this will have O of n cube. And similarly, this is going for I equals 1 to 3n square. So you can say this is going for O of 3n square. No, I won't write O of n3 square, rather I'll write 3n square. I'll say why. So these are time complexities, and for example there is another loop which is taking n time, we can just have it. So let's try to add up everything. So the time complexity for this test function would be, this is 2, plus this is n cube, this is 3n square, and this is n. Now let's try to recall the rules. The second rule was to drop all the constant multipliers. That means the constant multiplier is 2 here and we need to drop it off. So we just need to drop 2. Now second is we need to drop all the lower order terms. What all are the lower order terms here? So if there is n cube and we have n square and n, these are lower order terms in comparison to the whole polynomial equation. So why is that? Imagine you have n is very large, so which is the fourth rule, we need to take larger inputs. So when n tends to infinity, that means these all is nearly equals n cube. So 3n square and all these in terms of infinity are very minimal compared to n cube. So you can say it's n cube nearly, and that's how we can say its complexity is big of n cube. We need to take the highest order in that case, and this is the basically one of the examples. Now let's start off with finding time complexity for a recursive non-recursive function, and we'll start off with simple programs and we'll move towards more complex algorithm. Now this very example is a non-recursive code, and we can see it's very easy to find the time complexity for such a program. You can just count the number of loops and you can count the inputs, which are, the constants which are not dependent on the input, and things will be like this only. Now let's take another simple example before moving forward to a more complex program. Now this one here is a conditional statement. So the function has input n and a, and there is a condition. If a is greater than 1, there is an algorithm which takes O of n time, else the algorithm takes O of n square, and there is some constant terms as well. So what is the time complexity for this one? Take a while and try to come up with. Now I have seen a lot of people get confused with this simple thing, but when it comes to conditional statements, it's always applies the greater term. As per the rules only, if we say it is n squared plus n plus some constant time, we should take the larger input and the complexity will be O of n square, and that's how applies for the conditional statement. Now these are simple examples. Let's take a step ahead. So now let's take this example. So in this example, the value of I goes from 1 to n, and at every step the I increments, I equals I into 2. So it doubles at every step. So pause this video and try to figure out the complexity for this code. When we have a code like this, so let's try to visualize how the steps or how I jumps from one step to another till it reaches the final value of n. Let's say this is the timeline we have for I. I starts from 1. At second step I becomes 2 because I 1 into 2. So I becomes 2 at the second step. Now after that I becomes 4. It jumps 2 times because this into 2, again this multiplies into 2. Then it becomes 8, and similarly it goes on till it becomes n by 2 here, and after that only one step is needed to become n. So I jumps in a you can say quadratic way. For example, from 1 to 2, let's say this is a timeline 1 2 3 4 5 6 and like that 2 and n we have. So I jumps from 1 to 2, then here, then it goes here, then here, then it goes till n. So it jumps in a quadratic fashion. So now, if this is the case, how do you find the complexity of this one? The obvious answer is, if I jumps from one place to another in this fashion, so we can just calculate how many steps I took, the value, this is I, took to reach from the starting I position to the end n position, because it should go till I less than equals n. So these number of steps will basically give us the time complexity for the code. So let's start off with a very small input. So in this case, let's say the value of n is, say it starts from 1, and the value of n given is 1, and I starts from 1 as usual. So what is the number of iterations this operation is going to get called? So number of iterations this statement is going to run is for one time, right? Now let's take n equals 2. Now I goes from 1 and the total iteration this statement runs for one time. Then I becomes 1 into 2 and still it is within the boundary, so this becomes plus 1 and the total iteration becomes 2. Now let's take n equals 4 for example. So now I becomes 1, then becomes 2, 1 into 2, then 2 into 2 becomes 4, and this is the total number of values I can go up to, and this is the within the limits. So total number of times it will run is 1, 2 and 3. So this becomes 1 plus 1 plus 1. So this statement is going to run for 3 times. Similarly, if you take 8, it is going to run for 4 times. Likewise. So if you notice something, you can represent this I value as 2 to the power 0, 2 to the power 1 as 2. If it is 4, you can represent it as 2 to the power 2, similarly 2 to the power 3, and likewise. So now, we know if we have this kind of equation and if we go beyond, we will reach till, let's say, 2 to the power x, and the total number of iterations which is going to happen is x plus 1. Why is that? You can notice if 2 to the power 3 is the value of I, then number of iterations was 4. When it was 2, it was 3. Similarly, if it was 2 to the power x, total iterations is become x plus 1 iterations. So now, we know that value of I, this is I, value of I should be less than equals n, and this is the condition we have. So now, that means 2 to the power x should be less than equals to n, right? If that's the case, let's put log both sides, and it becomes 2 to the power x less than log of n. That becomes x should be less than equals log of n base 2. Okay, and that's one of the conditions we have. Now the total iterations is x plus 1. That means we can write x plus 1 iterations is equals log of n plus 1 base 2, and the complexity obviously it becomes less than this one. So in complexity analysis, if that's the case, we take the base condition and the complexity becomes log of n, and this is big O of log of n is the time complexity. Now that's one of the ways to visualize or write it down, but in general, if you want to, I mean, in interviews you're not going to always derive these things, so it's better to like visualize these things, like if the value of I is jumping from one place to another in a quadratic fashion, then it's a possibility that it is going to be a log solution. For example, there is a building, let's say the building is here and there are like multiple floors, and you're jumping from one floor to another in a quadratic fashion. So at every step you're getting the total distance is getting halved. So for example, if this is total length of the building is n, so at every step, at first step, suppose you're coming from top to bottom, it will be n by 2, then it will be n by 4, likewise. So you will jump at every step, the total number of iterations becomes half of it, and that's how you can visualize a log n solution. Now just before moving on to the recursive example, the last example which I just explained, let me give you another approach to it. So for example, as I mentioned about the visualization, you are till 1, then you jump to 2, then 4, then 8, likewise, right? And this is the timeline. So if that is the case, you can observe that this can be converted into, let's say, 1 step, then 2 steps from back, then 4 steps, 8 steps, and things like that. So if that is the case, and we reach to n by 2 plus n, right? And if that is the case, we can easily see it as a geometric progression. So in that case, so the formula becomes a r to the power n minus 1 by r minus 1, I guess, yeah. So this becomes 1 into 2 to the power x minus 1 by 2 minus 1, and so yeah, that's the case, and it should be less than n, so it becomes 2 to the power x should be less than equals n, as in before we discussed, and we saw if we append log on both the sides, So x comes out to be log of base 2n. And how important is base 2? Well, frankly speaking, not much important, but we'll discuss that how this base is getting affected. So yeah, that is one of the ways. Now let's start a recursive solution. So let's take this example, which is a simple factorial finding example. So given this program, which is to find a factorial of a given integer, so given a value is n, and if n equals 0, return 1, and then return n into the factorial of n minus 1. So let's see how do we write the time complexity for this. So as I mentioned, let's just write the fragments of it. So we know that this is a constant time which will take O of 1, and this one is calling n minus 1 times. So if the total function is taking t of n times, then this one is going to take t of n minus 1, right? It is being called by only n minus 1 times, right? So we can write t of n equals t of n minus 1 and plus this constant is 1, right? So now let's see how much is t of n minus 1 is going to call, because it's a recursion. So t of n minus 1 is going to be t of n minus 2 plus 1. Similarly, n of t of n minus 3 is going to be t of n minus 3, yeah, plus 1, right? So this is t n minus 2. So now if that's the case, let's just write it down. So t of n should be equals t of n minus 1 here, so it becomes n minus 2 plus 1 is there here, plus 1 and plus 1 of this one. So this one is basically t of n minus 1, right? So now we can write t of n minus 3 plus 1 plus 1 plus 1. So or I can just write 3, right? So you can see that if this is the case, we can go till t of n minus k plus k, right? So now what is the base case here? When n equals 0 and it will just return 1 and the time is just a constant time. So the base condition could become t of 0, which is become that is when the whole function is just like a constant function. So in that case, if this is the base condition we have, so n minus k should become 0, because we have to have this t of n minus k to become t of 0. So in that case, n becomes k. And if that's the case, so t of 0 and plus k is equals n now plus n. In that case, we can write t of 0 is equals 1 because it's returning 1 if n equals 0. So in that case, 1 plus n, or you can just write n. And that's the time complexity for this code. And you can see how this derivation has happened. Now, there are some people who are not much comfortable like to exclude and to take the base condition and just finding it out. But there are some other ways which we can use to find it out. Let's take another example and try to figure out what is another possible way to figure out complexity of such recursive function. So this equation is taken from another example of Fibonacci series. So in that case, here you can see it is t of n minus 1, n minus 2 and some constant. So that's the given complexity. Now how do you find for this one? So let's derive this. So let's say there is a function which takes like let's say f of n, and it makes call for subsequently. So if this function takes t of n times in this case, so the time complexity will be t of n minus 1, and second one it will be t of n minus 2, and there is some constant time as well. But let's ignore the constant for now and let's try to focus on this one. So n minus 1 again calls for t of n minus 2, t of n minus 3. Similarly, this calls 2 times, n minus 3 and n minus 4. And similarly, these things branches out, right? So if that is the case, you can see how many level depth this tree is going up to. So in this case, it is only one depth. It is level 2, level 3. So you can see that there are like 2 calls. Here it is happening 4 calls. It is happening it will be 8 calls like that, right? Which is equals 2 to the power 1, 2 to the power 2, 2 to the power 3 subsequently. And similarly this is for 0, so sorry, yeah, so this becomes 1 and this becomes 2 to the power 0, right? So if that's the case, again you can see the geometric progression. You can write in a way like you can write 1, 2 plus 4, similarly to the power n minus 1 like that. So if that's the case, again it's a geometric progression, and if you want to derive it, it will be 1, 2 to the power it goes to n minus 1, 2 minus 1, so the complexity becomes O of 2 to the power n. You can just do what I did showed you before. So now here's a pro tip. Whenever there is a function which makes multiple recursive calls, then what could be the time complexity for it? The time complexity is often, but not always, is going to be branches to the power depth. So let's say this is having 2 branches, and the total number of depth is going to be n, because it's going to be n layers as this is. So in that case, so total branches is 2 to the power n becomes the time complexity. And this is true not only for this Fibonacci equation, it can be applied for multiple branches. For example, there is a 3rd branch, 4th branch which is having similar kind of things. You can just simply apply branch to the power depth. So what is Master's theorem? So the original Master's theorem is a bit large and a bit complex, but for a starting purpose or for the interviews, you can just memorize this pattern, and usually with these kind of conditions you can simply find the time complexities. So any given equation of a recursive function or anything, you see an equation which is of this pattern. So if that's the case, you can simply put all these conditions, whichever is true, you can have the time complexity calculated directly. So let's take some examples and try to see how it comes up. So let's take this example. So example number 1. So you can see this is the equation, and we can see that this is a matching equation to this one. For example, this is n by 2, n by b, function of f is equals to 1, and stuff like that. So let's see what is the value of a here. So a is equals 1, you can write it as 1 into t. So a is equals 1. So now b is equals 2 in this case. What is the value of t in this case? There is no t basically. So t is equals 1 again. So that means log of a by b, which is log of a by b is 1 base 2, log of a base b. So that becomes 0. So the value of t is equals 0. And what is the value of c here? Because f of n is equals 1, that means n to the power c is equals 1. So that means c equals 0, because n to the power 0 days, right? So in this case, t is equals 0 and c is also equals 0. So that becomes, the time complexity becomes n to the power t log n, right? And t is equals 0, so it becomes O of log n base 2. Now here in the second example, we can see the value here for a is equals 1 as usual, because it's 1 into something. B is equals 2 because n by 2 here, b, and f of n is equals n here. So that means f of n is equals n, or we can see n to the power c is equals n, which means c is equals 1 in this case. So yeah, b is 2 and c becomes 1. Now t is log of a base b, so t is equals log of a is 1, b is 2, and which is again 0. So in this case t is less than c, so the time complexity becomes n to the power c as per the first condition, and c is again equals to 1, so that becomes big O of n to the power 1 or big O of n. So that's the complexity for the second equation. And the third equation, you can see this is something which is not matching the pattern of Master's theorem pattern. So here it is n minus 1 and it's not n by b format. So if that is the case, we can never apply the Master's theorem in this place, and that's the important point to remember. It cannot be applied blindly to any equation. It can be applied to only those equations where this pattern is a matching pattern. I think this is going to be it for today in this video. And in the next video, I'll be talking about the amortized time complexity, the space complexity basics and how do you find it. And also I'll be discussing about the inbuilt time complexities for some of the popular data structures. So let me know in the comment section below if you like the content or if you want me to make some more content videos or something improvements or any doubts you have. And yeah, till then, take care, see you, and do subscribe to my channel.